Ever wondered how electricians measure current without touching a single wire? These tools might look simple, but they're powered by the same principles that drive transformers and magnetic sensors. Let's uncover the science behind non-contact current meters and why they're changing the way we work with electricity. But first, it is essential to remember that before taking any readings with an electrical meter, it is necessary to verify the meter's operation on a known source. The current clamp meter is a non-contact current measuring instrument. The advantage of this instrument is that it requires no electrical connection to the conductor under test. This makes them inherently safer than contact-based current measurement devices. The AC current clamp works on the principle of electromagnetic induction, in much the same way as an electrical transformer operates. The clamp section of the meter contains a soft iron core that concentrates magnetic lines of force. This clamp is placed around the conductor under test. A conductor carrying AC current produces a magnetic field around the conductor, which expands and contracts continually at the frequency of the supply. The strength of this constantly changing field is proportional to the level of current travelling in the conductor. When the current clamp closes around the conductor under test, magnetic flux from the conductor circulates in the iron core of the clamp. Inside the clamp is an electrical winding wound around the outside of the iron core. The changing magnetic field in the iron core induces a voltage into this winding, proportional to the strength of the magnetic field. This voltage value is converted by the meter's circuitry and displayed as a current value on the meter's display. A more recent development is the DC current meter. Many modern clamp meters measure both AC and DC current. Modern DC-based electrical systems are now common in the industry, and a DC current meter is an essential tool for the electrical worker. The magnetic field around a conductor carrying DC current does not expand and contract like the field in an AC conductor. A DC conductor's magnetic field is static. So here, electromagnetic induction cannot be used for current measurement. The static magnetic field intensity remains proportional to the amount of current flowing through the conductor. The soft iron jaws of the current clamp provide a path for magnetic flux lines once again. A sensor called a Hall effect device is placed in the magnetic flux path and used to measure the strength of the magnetic field. The Hall sensor circuitry produces an output voltage proportional to the magnetic field intensity, and the meter's circuitry converts the voltage to a current reading on the meter display. Non-contact DC current meters have a zero set function, as any stray magnetic field in close proximity to the sensing element will influence the Hall device and affect the reading. The current fork meter is another innovation in non-contact current meters. Unlike the clamp type meter, this meter uses an open U or fork-shaped sensing component. When taking measurements with this type of meter, correct conductor positioning is essential. The conductor should be located at the bottom of the fork for the most accurate reading. Non-contact meters provide a quick, convenient, and relatively safe method for taking current readings. Like any electrical meter, clamp and fork current meters should be properly maintained and stored to prevent damage and extend their service life. Want to learn more? Check out our next video where we break down current transformers.